next is slightly more complicated. It's just an example. Right? We have two parallel wires, long, basically, we can say infinitely long, parallel, but and actually currents also in both wires, currents flow in the same direction. So I1 is up and I2 also is up. And on purpose, I use different colors, so green and blue. Some geometry is given. Let's say the length of these wires is L. And the distance between centers of these wires is D. And the question is, so basically all this given, I1, I2, DL are given, and we need to find the force, basically net force, right, acting on this current I2. Right. So we will find that force, but let me ask you before we even start discussing, what if I changed the statement of the problem, and what if I ask you, find the net force acting on the wire I1? Would that force be any different in absolute value, in magnitude? It would be exactly the same. Of course, a logical question, can you justify it according to what? Newton's third law. You all know that from physics 1, right? It's like the Earth and the Moon, they interact. And of course, forces that they exert on each other exactly the same in absolute value, in magnitude. But of course, opposite in directions, right? Force acting on the Earth from the Moon will be that way. Force acting on the Earth from the Moon is that way. And the force acting on the Moon from the Earth is this way. They will be the same in absolute value, but opposite in direction. The same here. These two forces are going to be the same, but opposite in direction. The same in absolute value, right? But I picked, let's find the force acting on the second wire, current I2, right? Okay, so of course, we need to decide, again, have a clear picture about the strategy of this problem. It's sort of like I already mentioned, I compared with the situation like generals before they start fighting, right? Start fighting some battle, then they have to have a clear picture. So first we go this way, then some troops will join us, and then this will join, right? So some rough structure must be in your head. So here we also must have something similar, right? Okay, so the question is about the force on a straight wire. So of course we will have to use this expression, this formula. Force acting on the straight wire with current I. And look at this formula. Let's have a clear picture. Which part represents what? I times L. These two factors, these two quantities, they represent what? They represent an object which experiences a force. Basically a victim, right? Because force, it's describe interactions, right? So one object interacts with the second. So in this case, it's an object, describe an object which experiences that force. Of course, in our case, it will be I2. It's our victim. Then B, of course, in our case, B right now is not given. But of course, we know that B is created, this B is created by some other external object which exerts force on the first one. Sort of like a bully, right? So this is the representation of a bully which exerts force, and this is our victim which experiences the force, who receives the punch, and the first one, and then the second one who punches, right? So now, as a result, we need to have a clear picture which object does what. In our situation, this is our victim I2, which experiences the force, and this is our bully, which exerts the force on the first one, right? And then, we will have to, of course, find the magnetic field which is created by this wire, right? Plug it here for the force acting on the second, right? So that's what we have to have clear in our head. Object which experiences the force and object which exerts the force. Okay, let me write that down like in my notes. All right, so let me write something like this. I will probably step out a little bit. So I, um, okay, let me write like this. So I1, this wire, okay, this current uh, is a source of the magnetic field, is a source. And you know what, let me use this comparison. It's sort of like a bully, right? Source of magnetic field, bull of source of B, right? Let me write B1. And um, it exerts force, a force on I2. Okay, let me frame it like this. State it like this. So it's a source of B1, and so can we write expression for the magnetic field created by the first current? Yeah, it's an infinitely long straight wire, basically, right? So we know the formula. We used it already many times, and you used it in your exam. I haven't graded that problem yet. So we can write that B1 equals to mu naught times I1 divided by 2 pi. In general, of course, it's a 2 pi r, where r is the distance from the center of the wire. But of course, for our particular problem, we will need to know the value of the magnetic field at the place where the current I2 is. So, and that distance is d, right? So let me use here d. And let me write also add a direction in the brackets. Like, probably first I should frame it because it's an important preliminary result. In direction, how can we find the direction of this magnetic field? Right hand rule number 2, right? So outstretch your thumb in the direction of the current, and on this side of the wire, magnetic field is going to be into the board cross, on this side out of the board dot. Or I can remind you so that magnetic field lines, they form something like this, right? So on this side into the board. Okay, let me draw a couple, 3. Of course, it's also over here will be, right? And on this side, dots. So that's our B1, direction of B1. And this is the magnitude of that magnetic field at the level, okay, at the distance d from the source of the magnetic field B1. Okay, so let me write it here into the board. Yeah, into the board at the place of I2. Because again, we want to find eventually the force, so we're interested what happens around the wire I2. Right? Okay, so now basically, what? Now we can forget about I1 because we know the information about the magnetic field B1. Right? So now we just this wire I2, which is exposed to this magnetic field B1. Right? So now we can just grab this formula and start applying it. So now it's the rest is straightforward. But you know what? I still want to write in words the role of I2. It's our victim, as I said, right? It's the force which experiences the force, which we wrote it I2, I2. Let me write. So it's sort of like a victim is exposed, exposed to B1 and experiences that force F2, a force which we call F2. Right? And of course, we can find that force F2 using our expression formula for the straight piece of wire. So I Okay, you know what? On purpose, which subscript I have to use, because when I start bugging students about this subscript, some students are not very confident. Although I already discussed that a few minutes ago. Here, this I and that L, they describe an object which experiences the force. In this case, it's a I2. So here I have to write the subscript 2. So it's a I2. And then the cross product of L and B1, right? Because so this current I2 interacts with this magnetic field B1, which we just described. And I guess again, I will just divide it into two steps, find direction and find magnitude. But you know what, again, before I want to emphasize that a direction of L is determined by the direction of the current. All right, let me emphasize on that. So it's a direction of I2. So direction of L is determined by the direction of the current I2 in this case. Okay, and so now let's find first direction of F2, right? And then magnitude. Direction, right-hand rule. L cross B. So everything is on the picture. Again, L is determined by the direction of the current. So the first vector in the cross product um, is up. B1 is into the board. You see B1. So I have to apply right-hand rule like this. So L, right? And then I have to orient my hand like this so that I can bend my fingers, you see, fingers in the direction of B1. B1 is into the board, right? So as a result, my thumb gives me direction of the cross product, which is to my left. So I can write, no, first let me draw it. So this is direction of F2, direction of F2. So I can write to the left. So it will be force of attraction. Yes, so the current I2 will be pulled towards I1. And magnitude, F2 equals I2 and absolute value of L cross B1. I pulled I2 outside, although I could have written this. I could have put this bracket over here. It's no big deal, but it's absolute value of the current, right? And so now let's write explicitly. So it will be I2. Then magnitude of first vector L. Then B1 and the sine of the angle between L and B1. So what's the angle between L and B1? Look at the picture. L, again, it's the direction of the current, up. B1 is into the board. So up and into the board, the angle you see, 90 degrees. So this is L, this is B1. So the angle is 90 degrees. Sine of 90 degrees. Sine of 90 degrees is just 1. Right? And of course, instead of B1, I'm going to use the formula which we just wrote a few minutes ago. Okay, I will start a new line. So F2 equals to I2L. And instead of B1, that's that mu naught I1 divided by 2 pi D. Okay, so basically this is the answer, but let me make it look nice. Let me just arrange these factors in a better way. So it will be mu naught I1 times I2 divided by 2 pi d, and L is in front. I want to arrange it like this. Because very often, or quite often, people are interested, if you have a situation like this, they're interested in the value of the magnetic force per unit length, basically per meter. Because we still had two infinitely long wires, right? But in order to solve the problem, we introduced this length, right? So in order to solve, in order to go through the calculations smoothly. But of course, since yeah, you're dealing with an infinitely long objects, right? It's better to talk about force per unit length. So how can we get that? You just take L to this side, and you will get force per unit length, right? Newtons per meters. Okay, which way I wrote that. First, let me frame this because that is effectively the answer, right? And or let me write or force per unit length. Right. So it will be what? F2 divided by L, it will be just a mu naught product of currents and divided by 2 pi d. Right. So quite often people might be interested in this. Because yeah, in industry there are plenty of situations when you have two wires, long wires with currents. Right. In this case, currents are in the same direction, but you can easily also discuss the situation when, for example, current I2 is down. And you can apply the similar logic, right? And of course, in that case, force will be repulsive. And there are plenty of videos where you have two wires, right? And when they drive currents, and of course, you can see that they get closer or they are pulled apart, right? But in order to see that, you need to drive a very large current, and I don't want to deal with large current. Very strong batteries and so on, especially at home. Okay, so that's what I wanted to discuss. And again, first you have to have a clear picture. Which object is the victim and which object is a bully, right? So which object experiences the force and which object exerts the force, right? And so basically two steps. First, you write find the magnetic field which is created by the bully, right? And then formula for the magnetic force, so which describes what what a victim experiences, right? Force exerted on the victim.